So let's begin with a few reminders about multivariate calculus. Actually, everything is in the power series expansion of a function. Okay, a very quick recap. Let's say that you're considering a function f that is at least differentiable in a neighborhood of some point a. Okay, and what we can get from the first order Taylor expansion of this function is the following. We can get a value, an approximate value of f at point a plus h, where h is a small positive or negative value. Okay, so this value, when we are located very close to a, is going to be, well, the first approximation is going to be the value of your function at point A, and then we've got this f prime of at point A times the displacement h, plus some reminder, which is the small o notation, which is a very small, very negligible amount compared to what's preceding. Okay, so that's the idea of the Taylor expansion, at least first order. And if you remember, well, we can write this as for x close to a. Instead of writing a plus h, we can write it as x. And this is what the expansion becomes. And you know that this part, that part, if you write y is equal to f of a plus f prime of a times x minus a, this is the best first order approximation, which is actually the tangent line to your function. All right. For functions of n variable, well, we've studied that in the previous years. What's happening? We've got something absolutely equivalent, well, looking very similar to what's preceding. So let's say that we are given a function f that takes n inputs. So you can always picture that it's R2 or R3, 2 or 3, xy, xyz, but it could be absolutely any finite amount of inputs, any finite amount of variables with real values. And of course, you know that your function is going to have as many partial derivatives as it has inputs. So let's just say that this is going to be these d partial df over dxi, and we are considering it at point at some specific point A, but this point A has now n components, and we are doing similarly a very small displacement in some direction h, and so n component for this direction, and the idea is that the norm of this displacement is remaining small. In that case, the value of your function f at a plus h, so if you start from your point A with those n components and do this small displacement in the direction h, you're going to have something very similar at what's preceding, meaning you've got first approximation, the value of your function at point A, and then the sum of the partial derivatives times the corresponding displacement, right? Plus something, a small o of norm of h, which means it's something very small compared to the norm of h, so compared to what's preceding, right? And again, this is the best first order approximation of your function, and this is well, if you have two variables, that would be the tangent plane to your surface in R3, but we have the extension of this idea. We can call that the tangent hyperplane. All right. So this is our first order Taylor series expansion. That's, I've rewritten here the same one as in the previous page. The good thing is that we have some great notation, that's gradient notation. So with this gradient shape called nabla, so the gradient of f at some point A, it's just going to be the column vector that contains all the partial derivatives of your function at point A. And so using this notation, we have a much more concise way of writing our Taylor expansion. It's going to be the value of f at a plus h, that's the same thing but written as a plus h instead of a1 plus h1 and so on. That's going to be first equal to best equivalent is going to be best approximation is the value of f at point A, so that's this part, and this the product of the sum of the product of the partial derivatives times the corresponding displacement, we can really write it as the dot product of the gradient of f with h1. Okay, so if we, because of h with h, if we write this is really going to be df over dx1 up to df over dxn, dot product with the displacement h1 up to hn, and that's really going to be, if you make this dots product, df over dx1 times at point A times h1, so that point is actually just a usual product, plus df over dx2 at point A times h2, etc. Okay? All right. So this is the first order Taylor expansion for my function at point A in a direction given by that vector h, right? Just one small stuff that we can see is what's happening when this h allows you to follow the level line of A. Okay, what's happening in that case? Let's see. If that h value allows you to remain on the level line of A, what's happening? So we are going to have f of A plus h, in that case, equals to f of A, if you are on the same level line. Okay, so that means that the gradients, that term, well, we will consider that this is very small, so this is negligible. It means that this term will be equal to 0. What does that mean? It means that in that case, the gradient of f is orthogonal, because the dot product is equal to 0, to the displacement h. Okay, so maybe we can try to visualize this. If we have some surface, let's say some nice smooth surface looking like this, and we are, let's say, on some specific level line, that will be the level line f of A is equal to some specific level L. If I'm staying on that level line, of course, the gradient is going, well, the gradient is equal to 0, because there's no difference between the value of f at A and the value of f at A plus h, if I'm staying on that green line. Okay, so the gradient is going to be orthogonal to this one. We can have a quick look at this GeoGebra page. So here we've got an example of a surface in R3. So that's the image of the function f of xy is x2 over 5 plus y square over 20, right? And so at some specific point, we are given the tangent plane, and we see that the gradient vector, well, it's not only orthogonal to the level line corresponding to the value chosen, but it's also orthogonal to the tangent plane, right? So if your point moves, here we've got a nice animation that shows how it behaves when the point that we're looking at is moving. So we really have that the tangent plane is moving along, of course, and the gradient is always going to be orthogonal to this. And of course, you know that we can go on our Taylor expansion as long as we want, as long as your function f is differentiable. So again, let's get back to what's happening in one dimension with one variable. This is going to be the best second order approximation. So you've got this second order term, which is 1 over 2 f second of a x minus a square. So I can remind you that the generic term being 1 over, so the nth term, maybe not n, let's take the kth term, 1 over k factorial, the kth derivative of your function at point A times x minus a to the power k. So you have proven this formula. So that's going to be the Taylor expansion of your function. You've proven this formula in year 1, and we saw it again in year 2 when we were dealing with power series. Okay, so, but for us, we just need it to go up to order 2, because this is actually the whole scope of optimization that we're going to deal with. All right, so that's your pattern for Taylor expansion. Of course, we're going to have something for functions of several variables. So for 2 variables, we saw that also previously for 2 variables. So you've got, again, so it's here, it's written in a neighborhood of some point with x0, y0. So f of xy, that's going to be best approximation f of x0, y0. Next term is the first order approximation term that we saw previously. So x minus x0 times df over dx, y minus y0 times df over dy. So this really corresponds to df over dx at x0, y0, df over dy at x0, y0. So that gradient vector times, so x minus x0, y minus y0. So this is the gradient of f at x0, y0 times, xy minus x0, y0. Okay, so maybe that could be a notation, maybe not the best one, but all right, so this is what you have here. And we've got a second order term where you're going to have, similarly to what's happening in one dimension, one variable, you're going to have 1 over 2 of your second derivative times the square of the displacement. So for us, we've got how many second order derivatives do we have? We had 2 df over dx, df over dy first order derivative, and you know that we've got 3 different kinds of second order derivatives: derivative up to x twice, up to y twice, and according to the x dy. And so that's going to be exactly the same pattern. If we're doing the derivative according to x twice, we multiply by x minus x0 square. According to y twice, we multiply by y minus y0 square. And according to dx dy, we multiply by x minus x0, y minus x0. But as we can do dx dy and dy dx, that's also the same thing. We have a 2 times here. Okay, so I hope you can remember it as a pattern, so it's not too, it's really no novelty, and we've used that many times. Okay, but you have to remember this pattern of function. The good news is, well, what's happening for n variables, we could, of course, write the same term, but for many variables. So, but you see that it's going to become huge very soon, because let's say that for 3 variables, you've got how many? You've got 6. How many second order derivatives do you have? According to x twice, y, and z. So you have, that's 3 different, and then you've got x, y, x, z, and y, z. So you've got 6 different second order derivatives. So you would have 6 terms here. And every time you've got a cross derivative, you would have 2 times like this one. Okay? So it's really something you could write, but we want more generalization. So this is where we're going to use some better notation, and something that we have also already dealt with, which is the Hessian matrix. If you don't remember about the Hessian matrix, never mind. It's just a matrix that contains all the second order derivatives. So for instance, if I've got 2 variables, my function f of xy, so how many second order derivatives? I've got the derivative according to xx to xy, and yx, y square. So what do we have in that Hessian matrix? d2f dx2, d2f dx dy, d2f dy dx, d2f dy square. And of course, this is going to be a symmetric matrix, as those 2 terms are supposed to be equal to each other. Okay, so, and if we've got 3 variables, of course, it's going to be absolutely doable again in 3 variables. You would have, if I call them xyz, d2f dx2, d2f dx dy, d2f dx dz, d2f dy dx, d2f dy square, d2f dy dz, then I would have d2f dz dx, d2f dz dy, and finally d2f dz square. So of course, and this is of course something that I could do in any number of variables, but if I've got n variables, I will have an n times n matrix. Okay, and we see as we still have Schwarz theorem that is valid, meaning that the second order derivatives it doesn't matter in which order you differentiate, whether it's with respect to x and y or with respect to y and x. It's going to be the same value if ever your function has continuous second order derivatives. Okay, so that's Schwarz theorem. So that this stuff here is equal to that one, and this one is equal to that one. So that's symmetric. Whatever the number of variables, it's something we can write, and we will always obtain a symmetric matrix. Okay, so that matrix containing all the second order derivatives is called the Hessian matrix. All right, and the good news is that we can write the previous expression of the Taylor expansion with two variables or even more variable. We could write it using the Hessian matrix. That's going to be this one. So what do we have here? F at x0, that's your function. We're looking at x0 as a point with n variable. Right? We're doing some increase. Let's call that k because we already have an h in the Hessian matrix. So let's call that k. It has also n components, k1 up to kn. So the value of your function at x0 plus k, so we're doing a small displacement in the direction of k, is f of x0 plus, we see the first order term, gradient of f at x0 times k, plus this thing, second order term, so that one 1/2 h of x at x0 times k. This one is really a matrix vector product. So you've got your H matrix times your vector k1, k2. Okay, so that's matrix vector product. And then we've got dot product again with the vector k. Okay, so that the result is really a real variable, a real value. Okay, plus the small o of k square, norm of k square. Okay, so something very small compared to what's previously written in the expansion. All right, and okay, so another way to write this stuff, the Hessian matrix times k vector dot product with the k vector. We can write it again with the inner product notation that we've used last year, maybe to be clearer about what comes multiplied with what, and what kind of multiplication we are doing at that point. Okay, so and actually this is going to be something, this kind of term here, that's what is called the quadratic form, and this is going to be of some importance later on. Okay, so this is the end of the reminder about multivariate calculus, and let's begin then optimization.